Alrighty. Hello, everyone. To those who joined, welcome to the first Echidna workshop streaming series. This is part one of six, and this is where we'll cover the basics of Echidna. So before we get started, I'm just going to talk about some housekeeping items. And while I'm talking, feel free to clone this repo and open the part one folder. So housekeeping item number one, if you do want to follow with the interactive exercises that we have in this part, make sure you have Echidna downloaded and installed, and then you can do so. If not, the repo will be public. It's live. You can always pull it down whenever and do the exercises on your own time. If you can't type it in time or whatever, the critic repo is linked at the bottom of the screen over here, so you can always get it from there. Additionally, just note that we're updating the parts as we go along. So if you are an eager beaver and you want to do part three, just know that all the stuff might not be in there for part three yet. So just keep that in mind, but it will be over time. So just an FYI. And all of this stuff will be moved to building secure contracts, which is a repo we maintain on Trail of Bits. So everything that we do from parts one through six will move in there, but we can touch upon that at the end of this workshop. Okay, so like I said, this is a part one of a six-part series. You guys will be back with me again for part two, where we'll talk about fuzzing arithmetic functions as well as functions in general. And then we have the intermediate section, which will be parts three and four, and then the advanced sections in parts five and six. So a lot of exciting stuff coming up in the near future. So who am I? My name is Anish Naik. I'm a security engineer at Trilla Bits. I primarily focus on Ethereum security audits, primarily in Solidity, and I'm trying to improve my knowledge base in a few other code languages as well. I also do a lot of public speaking like this one on Echidna and also provide some development help on a few of our open source tools. So I put my Twitter link, but I don't really post that much. So I added this section of who you should actually follow at Trail of Bits. Troy Sargent, Jocelyn Feist, Nat Chin, and Justin Jacob, all incredible team members. And so they do post a lot of interesting security content. So you should definitely check them out. By the way, Jocelyn and Nat are both on the Twitch and YouTube streams. So if you have any questions with the help fixing up Echidna, downloading it, or any general questions, they'll be there to help. I'll also be intermittently taking any questions as they come along. So we all work for Trail of Bits, and Trail of Bits is a security company that's specifically focused with research and development. And so we not only do auditings, we work with public sector clients, we work with just general applications, not in the Web3 world. So we do a lot of different things. And what's really cool about Trail of Bits is that we're research and development focused. So what that means is we like to push the envelope in security. And one of the ways we do that is we build a lot of tools. So in the smart contract or Web3 ecosystem, we have a lot of tools that are popular in the industry, such as Slither, Echidna, which is the topic of today, Tealer, Amarna, Solk Select, and there's a bunch more as well. So yeah, that's just a little bit of me and of our company, and we can get started and look into the agenda for today. And so we'll talk about a few different topics. The first thing we'll touch upon is how to find bugs, and we'll look at the different methodologies you can employ to actually find bugs. We'll then look at what fuzzing is and how that fits into the testing methodologies. Then we'll look at some interactive exercises where I'll actually write some code up and show how to use Echidna to do fuzzing. And then we'll close up with talking about how to define good invariants. And this section will kind of set us up for the next week's workshop, and then we'll conclude and look into what we'll actually do for next week. Awesome. So how to find bugs. So let's here just given this like snippet of code. Let's just say it's some part of a bigger token system or whatever. And you have this buy function that takes in this tokens amount. And what it will do if you want to buy some number of tokens of this ERC20 system, it'll first check whether the amount of tokens you want to buy is valid. And so the way this is done is by calling the valid buy internal function. And what you need to provide is 1/10 of the amount of tokens you want to buy. So let's say you want to buy 100 tokens, you have to send in 10 ether to do so. If you do, the buy function will then mint message.sender the number of tokens. If not, the transaction will revert and you don't get any tokens. So the exchange rate here is 1 ether to 10 tokens. Now, obviously, I'm showing this piece of code because there is a bug in it. And we'll kind of go through this journey together to see how Echidna can be used to find this bug. But before we do that, we're going to talk about the other different testing techniques that you can use to find bugs in general or the bug in that specific snippet. So we have unit testing, manual analysis, fully automated analysis, and semi-automated analysis. So unit testing, the main benefit is well understood by developers. It's well known in just the general programming world. But the limitations are that it mostly covers the happy paths. So when a developer is writing unit tests, they'll think of the expected values that the unit test should cover. They'll test that, and if those unit tests pass, then you're in the clear. But that leads to the second limitation, which is that you might miss edge cases. So you might not test the unexpected values, which might lead to the unexpected edge case. So for example, if you have this unit test, you'll notice that the two values, tokens to receive and ether to send, are concretized. They're set values. And if you run this, you'll call the buy function, and you'll assert at the end that your new token balance is your previous balance plus the tokens to receive. And this will pass because the exchange rate of 1 to 10 is passed. You have 100 ether and you want 1,000 tokens. That's great. It'll be okay. Now you can run this unit test and say, great, my function works as expected. But the issue with unit testing is, if you think of the input space for any system or smart contracts, let's say, to be a line from 0 to infinity, a unit test is just a dot on this line. It just tests one concrete set of values. Now you can test a few different concrete set of values, so now those are a few different lines, but you're unable to get the breadth in the entire input space, and that's usually what leads to edge cases that can't be found through unit testing alone. So you could also find bugs through manual review. And the benefit of this is, theoretically, you can find every possible bug in the code base. The limitations, however, is that it's really time consuming, it requires a very specific skill set, and it does not track code changes. So an example of manual review would be a security audit through any firm. And the security audit is great. You do it today with how much ever code you have. Awesome, you have your results. But now let's say the code changes, and in 6 months you want to look at your security posture. You'll notice that the security review that you did 6 months ago, the issues or findings don't really apply anymore because the code has changed significantly. So that's why we say security audits are a snapshot in time. It assesses your security posture today, but does not track what will happen if your code changes significantly in 6 months or a year, whatever it may be. So then we have fully automated analysis, which is, the main benefit is really quick and easy to use. An example is Slither, which we at Trilobits develop and maintain. But the limitations is it can only cover some classes of bugs. So Slither is really good at, you just enter a command, you let it run, and so there says, okay, there's possible bugs with, class X and class Y a bug. But the issue is Slither can maybe not find classes X or sorry, class A or class Z a bug, whatever it may be, right? So although really fast, it has some limitations on how many different types of bugs it can find. And then this kind of comes in the topic of what we're going to talk about today, and then for the future workshops, is semi-automated analysis. And the benefit of semi-automated analysis is great for logic-related bugs. It's great for those hard-to-find bugs that can't be found or may not be found as easily with the previous testing methodologies. The limitation, though, is that it requires a human in the loop. It requires someone like you or me to look at the code and say, I need to guide the automated piece such that it can do its job well. And that's sort of the example here is fuzzing with Echidna. That's what Echidna is. It's a semi-automated analysis technique where you as the human tell Echidna to do certain things, and Echidna can do those things really well. So I do want to caveat here that all four testing methodologies are incredibly critical to any code base. It's not that one is superior to the other. They all have benefits. They all have limitations. So you have to have high unit test coverage. You should definitely do security reviews. You should definitely run Slither and use CI. And you should also, mature code bases will also have fuzzing with Echidna or fuzzing in general. And that's really how you improve your security posture and do defense in depth. Okay, so what is fuzzing? So fuzzing at a high level is just kind of 3 steps. You generate a random input and you test something. The something we can define a little bit more concrete in a little bit. But you test something, and then if the input that you're testing the something with fails, then you log that and tell the user, hey, I found something that broke the thing you care about, the thing you're testing. If not, you restart the cycle and you try a new input and you test the something again. And so this is the kind of cycle of fuzzing at a very high level. Now, the something that you test is a kind of an interesting piece, and it's very different when it comes to traditional fuzz testing versus Web3 fuzz testing, let's say, or property-based testing is what we'll call it right now. So traditional fuzz testing is well established, And the main goal is to stress the program with random inputs. So here, the input to the fuzzer is sort of just this binary or this application, and you throw a bunch of random inputs at it. It's like basically smashing your keyboard really fast, and the goal is to crash the program. Now, that doesn't really apply to smart contracts because smart contracts don't really have crashes. For example, if I send a transaction and the transaction reverts, it's not because the smart contract crashed by any means. It could be because I didn't provide the necessary allowance or whatever else, right? So a failing transaction doesn't mean a failing smart contract. Smart contracts don't technically have quote unquote crashes. So we want to still employ fuzzing though. So like how do we approach that in the smart contract world? And so this is where property-based testing comes in. Now you can do property-based testing with fuzzing. You can also do it with other formal methods. But for our context, for this discussion today and the future workshops, when we say property-based testing or property-based fuzz testing or fuzzing, it all kind of means the same thing because we're in the smart contract realm now. And so with property-based testing, what you do is you define some properties. So the test something, the thing you're testing is not just some application, it's properties. And if you're confused about what a property is, we'll define it in the next slide. But the fuzzer still generates a bunch of random values. But instead of trying to crash the program, the fuzzer will try to test the properties and validate whether the properties hold or do not hold. And so what you're trying to really test is whether the system is expecting as you think it actually does. And that's where the human comes in. The human has to define the properties and say, hey, fuzzer, you're the automated part. Do the stuff you're good at. I'll tell you what to actually hit, and go ahead and let me know if something sticks. So what's a property? A property or an invariant or invariant testing, property testing. I'm going to use them interchangeably, and in future workshops as well. They're all interchangeable. The definition of a property really is something that is unchanged by specified mathematical or physical operations. And in our context, it's something that should always be true. And it should always be true given some preconditions. So I've italicized that part. And this is, again, just kind of a precursor to what we'll talk about later in this workshop and in future ones. System properties should always be true given some preconditions. So precondition is something that like basically creates a barrier as to when the property should be true. So for example, you have the transfer function for some token. If you're transferring from A to B some amount of tokens, the expected behavior or the property that holds true for the transfer function is that A's balance should go down by whatever, and B's balance should go up by that same amount. Now, this is only worth testing, or this is only true if A has some tokens to spend in the first place, right? So that's a precondition that given A has some tokens, the transfer function should show this behavior. So when I say system properties, what I really am trying to emphasize is we're trying to figure out the expected behavior of the system. You have a system property basically says, I expect the system or this function or this line of code to behave like this. And what we're going to do with Echidna is to actually test whether that's true or not. So an example invariant is that the user balance, again, this is an ERC20 token, any user's balance should never exceed the total supply of the token. And this makes sense. If the total supply is the sum of all user balances, there's no reason why any user's balance should ever exceed it. If it does, there's probably a bug in the code. So we've now talked about what an invariant is and what properties are, and what we're trying to achieve here is using fuzzers to create random inputs and then test these properties. And so that's exactly what Echidna does. Echidna tests system properties. And it's a fuzzer that will generate the random inputs and then test the human in the loop. It will test the system properties that has been defined by the human in the loop. And so it's completely open source. You can find it at that link. And we use it heavily in audits all the time. And you'll notice that a lot of the mature code bases out there also use Echidna. So how does Echidna work? Or what are the things that Echidna needs to function as expected? So Echidna needs two things. It needs a target contract and properties to test. So the target contract is sort of what Echidna is actually fuzzing. It's the target system that Echidna is actually hitting with, with various functions and inputs and all that stuff. And what it's actually trying to test, though, are the properties. So Echidna will hammer out some stuff with the smart contract, and then it'll come and check, say, okay, did I violate any properties? Or is the system is working as expected? And so you provide those two inputs, and then you ask Echidna, can you break the invariant? And that's sort of what Echidna's job is. It needs these two things, and with those two things, Echidna can now actually try to validate the things that matter. Okay, so now we're actually going to do some interactive exercises. But before we do that, I want to summarize sort of what we talked about. The the question or the problem statement is how do we find bugs? And we looked at a few different ways of doing that. And today we're going to focus on semi-automated analysis. And Echidna is one tool that you can do semi-automated analysis with. And the goal really is to try to figure out properties that describe your system behavior. And then you use Echidna to try to invalidate the system or try to validate or invalidate the system behavior. And the reason we do this is because property-based testing is really good at first validating system behavior, but also finding those logic-related or hard to find bugs in your code base, and is better at doing that stuff relative to the other testing methodologies we talked about. Okay, so I'm gonna check if we have any questions. I think we're in the clear. I'm gonna take a quick water break, and then we can get into the exercises. Okay, so before we get started on the exercises, I want to highlight some key considerations. So things I wish I knew when I first started using Echidna, and I think it would have really helped me when I first started using it. So think of Echidna as an externally owned account. And what I mean by that is think of Echidna just like your EOA or my EOA, except what it's really good at is at doing transactions really, really fast in an educated fashion with random values. So it's basically just message.sender. It's just sending out a bunch of transactions really fast in an educated way. So that is really a critical piece, and you'll see sort of how this plays in when we look at the exercises together. And so Echidna does the following. So it's an EOA. It's going to send a bunch of transactions, and this is how it does it. It'll call a sequence of functions with random inputs in the target and inherited contracts. So two things to highlight here. First, a sequence of functions. So Echidna can call a single function and then check the properties, but Echidna can also call 10, 20, 50, 100 functions in a row with random inputs. And then it'll do that in both the target and inherited contracts. So let's say your target contract, which is one of Echidna's inputs, is target or contract A. But contract A inherits contracts B and C. Not only can Echidna call everything in target A and maintain the state in target A, but it can also call all the public and external functions in B and C and also inherit all the state of B and C. And so you can really use inheritance in very interesting ways with Echidna to empower the fuzzer to do really interesting tests. And this we'll kind of see in the examples, and we'll really see the value of it in future workshops as well. And so, okay, Echidna calls a sequence of functions with random inputs on the target, and then it'll check whether the property holds. So it's basically a two-step process. Echidna will call a bunch of stuff. That's the fuzzing part. And then the property testing part is saying, okay, is the thing that the human asked me to check, is it still valid? If so, great. If not, I'll let him know. And the last thing I want to highlight is that properties just resolve to a truthy value. What I mean by a truthy value is that it resolves to a Boolean. Properties are just like system truths or expected truths. And so when you think of properties, just think of them as this should be true, or this must equal this must be greater than this. It's just things that can resolve to a Boolean true or false. And thus properties are usually prescribed as just Boolean statements. And we'll look at that in the exercise as well. Okay, so I'm going to move over to my VS Code in a sec, and we're going to look at exercise 1 together. And the goal for exercise 1 is to check for correct arithmetic. And so we're going to be using Solidity 0.7, which will provide you a hint as to sort of what we're going to be looking for. But let's go ahead and check out the README and see what we need to do. Okay, so here's our target contract. We have this token contract, which inherits Possible. Possible inherits ownership. And sort of, we can already see the inheritance pattern coming up over here. And really what we're going to care about for exercise 1 is the transfer function here. The transfer function basically sends some value tokens from message.sender. So it'll subtract from message.sender, and it'll send it to the to address, that same value. And here's our goals. The first goal is to add a property to check that Echidna caller cannot have more than an initial balance of 10,000 tokens. Note that right off the bat, Echidna caller here is Echidna, right? We talked about how Echidna is just message.sender. So we can treat Echidna caller as basically message.sender. So we can rephrase this property to say, or this goal to say, add a property, check that the message.sender, the guy who's sending the transactions to the target contract, cannot have more than an initial balance of 10,000 tokens. Once we do that, we're going to fix the bug, or find the bug, fix the issue, and then recheck our property with Echidna. So let's do that. Again, really the focus here is the transfer function, right? Properties are things that we say we say that matter, and Echidna's job is to basically validate that. Okay, so what I'm going to do is I'm going to create a new file. I'm going to just save it as anish.sol. Doesn't really matter what it's called. We're going to set the solidity version to 0.7. Um, we're going to do import token.sol. So we're going to import token.sol because what we're going to do is we're going to create this test token contract, which is going to inherit token. And so right off the bat, we're doing two things. We've defined the target of Echidna, so that's one of its inputs, its test token. And we've also used inheritance to our benefit. Here, what we're doing is we're saying because test token inherits token, we get all functions from token, possible, I'm not going to write it all out, from token, possible ownership, and we also get the state from those various contracts as well. So now we have the entire system at our hand because we inherited the entire system with our target contract. Okay, so now we're gonna do something I call setup. And setup is basically the things you have to do to set up Echidna in the right state to actually test your properties. And so the setup here is defined over here. Echidna caller cannot have more than an initial balance of 10,000 tokens. So how do we check whether Echidna caller can have more than an initial balance of 10,000 tokens if we don't at least give it 10,000 tokens to start? And so that is the setup for this example. So we'll say constructor. And in here, because we inherited token, we have the balances mapping. And we'll say balances, or sorry, what I first need to do is actually need to define Echidna caller. So let me do that first. So we're going to say Echidna caller is just message.sender, right? And that we already talked about this. It's the EOA that's calling this contract, which is Echidna, which is message.sender. And so the balance of Echidna caller is 10,000. And so right off the bat, we have the setup done. And so we've set up Echidna for success really by saying, look, we have this Echidna caller guy. He or she's going to have a token balance of 10,000. And now we need to provide Echidna the second input, the properties, right? Property or input number one is a test token. We have the setup done. And now we need to provide the properties that Echidna should care about. And so when writing a property for Echidna, it needs to follow the following format. It has to be a function. It has to have the function signature format echidna underscore asterisk, or the wildcard. It could be anything here. It could be whatever set of words you want. It takes in no functions. It's a public function, and it returns a Boolean. So we can see a few themes here. First of all, why does Echidna need this certain structure? So when Echidna calls these contracts, what it will do is it'll check all the state changing functions or view functions and say which of these functions has this Echidna underscore wildcard structure, and it returns a Boolean. When it finds these functions, it says, oh, this is a property. This is my second input. I'm going to store this in a different data structure. And these are the things I will call after I call a bunch of random functions in sequence. So this is how you tell Echidna, hey, this is what I want you to care about. I want you to find these functions when you're compiling the contracts and store them and call them at the end of every sequence of functions you call. And the reason we return a Boolean here is because that's what a property does. A property is either true or false. So if the computation in the function returns true, the property holds. If the computation in the function returns false, the property does not hold. So with that in mind, let's write our first property test together. So we'll do function echidna underscore, we'll call this test balance, takes in no arguments, and it returns a Boolean. Okay. And what I'm challenging Echidna to do is I believe that Echidna caller's balance will always be less than or equal to 10,000. And now Echidna's job is to first either validate this or find me the edge case where this is not valid. So here what I'm saying is balance of Echidna caller is less than or equal to 10,000. So that's the truth I believe. And Echidna will either validate this or let me know that maybe I need to look at my code a little bit further. So let's go ahead and run this. I'm going to move this up a little bit. Okay. I'm going to first use Solc select to set up the right solidity version. Solc select is one of other tools really useful for these kind of situations. And then we're going to call echidna test, which is the binary for echidna. I'm going to say, Echidna, I need you to compile everything in anish.sol, which is a file, not a contract. So Echidna will compile everything in anish.sol. But your first input, your target contract, will be test token, which is this guy right here. So that's your first input. And the second input, Echidna will figure out when it starts parsing through all the state changing functions and says, oh, this one actually is not that. It's actually a property because it has the function signature that I'm looking for. And that's how Echidna gets its second input. So it has both its inputs, and now we can run it, assuming I didn't write anything wrong. Echidna will find a bug. So the sequence that Echidna calls, the sequence of functions, it really just needs one here, it seems like. It calls the transfer function to some address, and it sends a huge amount of tokens to that address. So the first thing to do here is to say, okay, well, what's wrong with the transfer function? So let's go check it out. So the transfer function here will subtract some value from mesh.sender or echidna caller and add that to the to address. But remember, we're in 0.7.0, which means that safe match checks are not enabled by default. So underflow and overflow happen silently. And so what happens here is it doesn't really matter what the to address is. If I send a value that's more than 10,000, which is what I gave in the setup, to echidna caller mesh.sender, it'll underflow, and the resultant value will be more than 10,000. And that's how Echidna was able to find the arithmetic overflow or underflow in this case, in this piece of code. And so the next goal we had was to fix it. And so just for the sake of time, I'm just gonna explain the fix. I'm not gonna type it all out, but this is what the fix would look like. Just know that we're not recommending you do it like this. There's a lot of better ways to to fix this. You probably shouldn't be using Solidity 0.7 in the first place. That could be the quickest fix. But for the specific example, the fix is take the balance of mesh.sender and the to address beforehand, then actually do the transfer and make sure that the new balance of mesh.sender is less than or equal to the previous one. Because when you're subtracting a positive value from a positive value, the resultant value should be less than the original. But if it's not, that means you underflowed. And a similar argument can be made for the to address as well. For here, in this case, we're checking for overflow, not underflow. Okay, so that's example one. And now you might be thinking like, all right, I guess I kind of get it, but what's the point here? So that's a fair question. And what I want to emphasize here is this property, sure, it's concretizing this value. And it's like, okay, well, so what? What really matters here is what we're testing is more important than just more than or less than 10,000. What we're testing here is, can Echidna caller steal funds from the system? Can they just make magical money appear out of nowhere? Can they steal, can they like violate the property, which is if you have some initial balance, how are you getting more money out of nowhere, right? That's sort of what we're testing here in an indirect fashion. So although it's a little bit of a toy example, realize that like this is the same stuff that we do on audits. We always check, can someone steal funds? And right here, we're checking, can someone steal funds? So that's sort of the value here. And we've talked about sort of how you can look at the call sequence, debug the issue. We've looked at how to actually run Echidna on a target contract and provide properties. And so, yeah, that's the end of exercise one. I am going to move over to my slideshow. We're going to talk about exercise two, and I'll also check if we have any questions. Okay, so this is the template that we set up. This is the setup of the exercise. Here's a solution. We set this property, and Echidna breaks it because it sends a value more than 10,000, which causes the underflow. Okay, let's see if we have any questions. Okay, so the first question we have is, can Echidna validate raw bytecode or only Solidity? So Echidna needs an ABI at least. So if you provide the bytecode in the ABI, that's pretty much equivalent. So yeah, you start from Solidity, you compile it, and since you have an ABI, you know what the state changing functions are, what parameters it needs. So you need an ABI in addition to the bytecode to be able to do it. Obviously, the EVM works on the bytecode, so the bytecode is one part, but you also need the ABI to be able to figure out what functions I can call and what input parameters they take. The next question is the contract state reset after a sequence of functions calls? It looks like someone, I think, in the chat already answered this. Yes, it is. It's reset after a sequence of calls, except for the things that were constructed initially. So whatever you do in the constructor will persist, but any state changes that happen after construction, in let's say the 100 function calls, will be wiped, and then you start with a clean EVM state. Is there a way to use Echidna with pip Python, same way Slither is used instead of running the Docker image? Yeah, so yeah, it looks like we already have an answer for that. You can use Homebrew on Macs. There's a variety of different ways, and all that information should be on the Echidna README. And you can always come on, open an issue if you have any problems on the Echidna issue tracker, and we can help you if you have any issues with that. Okay, exercise 2. Let's get to it. So same exact token setup, but this time we're checking for access controls, right? So again, this comes back to the idea of what do we care about? We tell Echidna what to care about. If I never wrote the transfer function test in the first place, and I just did this, Echidna would never find it. So now our goal has changed, or our properties that we test are going to change as well. So let's look at exercise 2. Oops. Same system, but let's look at the possible and ownership contract in a sec. But our goals here, the first thing is the setup. Consider pause to be called the deployment and the ownership removed. So our setup is we're going to pause the contract, the target contract, and we're going to revoke ownership. So let's actually let's see what that actually does. So we have this pausable contract. The modifier is not particularly relevant here, but you can either pause the system if you're the owner, and you can resume the system if you're the owner. If you pause the system, is pause becomes true. If you resume the system, is pause becomes false. The ownership contract basically sends the owner to message.sender. So again, because Echidna deploys this system, Echidna is also the owner of this system. And so, oopsies, Echidna is also the owner of the system. And that's why we can first pause the system in the first place. So when Echidna deploys this, Echidna is the owner. And then in the setup, what we're going to do is we're going to pause the system, which makes this pause true. And then we're going to revoke ownership. We're going to set owner to address 0 or whatever. It could be dead beef, whatever you want it to be, right? And we can do all of this again is because we're inheriting this whole system when we deploy this target system, which we're going to call test token again. And then our next goal is to add a property to check that the contract cannot be unpaused. So our goal, or the thing we believe, the property we believe to be true, is that once paused, and since no one's the owner, address 0 is the owner, no one can resume the system. Because if you were to resume the system, you were somehow able to take ownership, and that's something that we don't believe can happen. And once we find the bug, we'll fix the issue and we'll retry our property. I didn't do that for exercise 1, but trust me, it works. Okay, so let's actually go ahead and do this for exercise 2. We're going to first do the setup and then go from there. All right, so I'm going to make, again, we'll just call this Anish Naik. We'll set the Solidity version here to 0.8. Doesn't really particularly matter. Import the token again. Let me show the reason I can import this here is just to show the layout. The token.sol is in here. So token.sol is the same thing I showed in the README, but just it's an actual Solidity file. Okay, that's a aside. So we import the token.sol. Contract, test token, this token, inheriting, so a lot of power. And now let's do the setup. Constructor. And what we're going to do is we're going to pause the system as requested, and then we're going to set the owner to the 0 address. Note that we can't do this in reverse order, because if I were to revoke ownership, I can't pause the system because Echidna no longer has ownership. So we pause it, revoke ownership. So now we're in a place where system is paused, and there is no owner of the token system. There is no token owner. Now let's write our property. Same thing, function Echidna. We're going to say test pausable. We could say test access control, whatever you want. It's public, it returns a Boolean. And here, all I'm going to say is I want you to prove to me that is paused is false. And the reason I can do this is all it is. It might seem a little jarring, but if you check the paused function, is paused is true. So the way I can test for pausability is by just checking the is paused value. So is paused is always true. And the only way I can invalidate that is if I make is paused false. But to do that, I must have taken ownership somehow. Otherwise, I wouldn't be able to pass the isOwner modifier. And so by setting, if this ever becomes false, we were able to take access of the owner and then unpause the system. And that is what we're challenging Echidna to do, because currently I firmly believe there's no way for the system to be unpaused because the system is paused and we revoke the ownership of Echidna. So let's try it. Go to exercise 2. It's over. Change the solidity version. Okay. In the test, and I want you to compile everything in this file, where the contract I want you to care about, though, your target contract, is test token. And again, when you parse the solidity, when you parse the code, make sure to find everything that I care about, which are these properties that have the specific format. Okay. Run it. And here we go. Echidna found a sequence of calls that was able to make isPaused false. So what does Echidna do? Echidna calls owner, and then it calls resume. So let's go check out the owner. Um, what happens with the owner function is that the owner becomes sender. And so right here, Echidna, because it called this function, was able to take ownership of the system. And now because it's the owner, it can call resume and unpause the system. And so this is the beauty of Echidna, is that it can do these sequences or these calls in sequence. Echidna is able to do these stuff in sequence and cause the system to get into a state where now it was able to identify a bug. If you just called the owner and then checked this paused, it wouldn't work. You would have to call them in sequence. And so that's, if you called owner and wiped the state and then called resume, it wouldn't work, right? You have to call these in sequence on the same EVM state. And so here we go. That's sort of how Echidna found the second bug. And again, you might be asking the question, well, so what? Well, we're kind of testing access controls at a more general level here, right? We will do the same thing in audits. We would say, okay, I have all these privileged actions. Can I, as the user, uh, uh, somehow get ownership or get a privileged role by doing some fancy stuff? So again, all super applicable for real world code bases, and we'll see more of these kind of things in future workshops. Okay, I'm gonna do a time check. Okay, now I want to take a slight detour and provide sort of a setting stone for another form of testing, which we call assertion testing. Now, before we do that, I want to highlight again that property-based testing is more general than assertion testing, or what we call this. This is what we call, in Echidna terms, property testing. And then we also have something we call assertion testing. But they're both doing the same thing. They're testing properties. The way they do them, though, is different. In property testing, you provide these kind of function hooks for Echidna, and Echidna will take everything in here, and at the end, a Boolean is returned. If the Boolean returns true, great, property valid. If returns false, property is not valid. In assertion mode, you do something a little bit different. Here we'll just call it test possible, public. Doesn't really have to return anything because it's a different mode. It doesn't look for these kind of function signatures. And all we're going to do is assert isPaused. So same thing, we're asserting a property versus returning the property, really. And that's kind of the main difference. So assertion mode also has additional benefits. I can take in arguments here because this is just a regular function. Echidna doesn't treat this in any special case like it treats this function. You can get a lot more flexibility because you can take in input arguments. And now this is an input argument, which means Echidna can fuzz this value, and it can make it anything between 0 and UN256 max. So that's all I'm going to talk about assertion testing. And the way you would run it in assertion mode is you could just do, we don't really need this, is we'll write the same line, but we'll just specify test mode as assertion. And same thing, owner resume. When you call test possible, you break the assertion. Note that the property mode is the default test mode for Echidna, which is why I didn't have to specify it here. But test mode assertion is more unique or different, so we have to specify it. Okay, that's the end of exercise 2. Again, the 2 exercises is really just about understanding how to run Echidna, how to write properties, or what a property really is, how to understand what a setup is, and just looking at sort of how you can abstract these simple examples into real world code and saying, okay, we do care about loss of funds, we do care about access control, and you can take these same principles and apply them in more realistic fashions that aren't these toy examples. The slide deck says the same stuff. It's the template. This is the setup. This is the solution. And Echidna calls owner and resume, and boom, we find the bug. Okay, I'm gonna pause for questions and do a water break. Got it. Okay, so how does Echidna compare to Foundry in terms of speed, underlying functionality, and or how smart is it with choosing inputs, like checking for special values? That's a great question, and I guess there's a few different I have a few different points to this. So Echidna is definitely more mature at the time with when it comes to its features. Echidna is definitely more feature rich when it comes to that aspect. Now we definitely don't have the same level of capabilities when it comes to VM.prank or cheat codes and stuff like that. So it really comes down to the trade-off of Echidna focused first on trying to provide as much capabilities and power to the end user, whereas Foundry took a slightly different approach and made some decisions to make it slightly more developer friendly along the way. Um, in general, though, I think there will be at some point some level of feature parity. But at the moment, Echidna does some stuff that is a lot more unique than what Foundry does. For example, the way Echidna will determine its next sequence to call, it'll use something called its corpus. So Echidna will call a bunch of stuff, and if that stuff is interesting, Echidna will store that sequence of calls. And when Echidna does its next sequence of calls, Echidna will say, okay, you know what? With 80% chance, I'm going to try a completely fresh set of calls. And sorry, with a 20% chance of fresh set and an 80% chance, I'll use something from the corpus. And when you use something from the corpus, you're using something that has already shown to provide value to the fuzzer. So Echidna will take that, it'll mutate it with certain changes in the parameters, and then try it again. And maybe it'll append something in the middle of the transaction sequence, or something at the front or in the back. And that is something that's really unique. And now that new sequence can maybe provide more coverage or more depth into the code base, right? So from a feature perspective, Echidna definitely has the leg up. Will that be true in I don't know how long? Maybe, maybe not. And our development team is also trying to make Echidna more developer friendly because we do know that there are certain things that Foundry does that Echidna can't do, like the pranking and stuff like that. But there is a risk when you have stuff like pranks and stuff like that. You might have divergence from the underlying, EVM client or whatever it may be. So still an open question, but in general, Echidna is definitely more feature rich at the moment. Um, okay, let's see if there's any other questions. Okay, yeah. It looks like there's a list of answers, I think, to the question in the. Okay, yeah. Cool. Yeah, so another example, I guess, of how Echidna can the one feature that Echidna has specifically compared to Foundry is Echidna can also fuzz block timestamp and block number. So it's not just sequential where if your timestamp goes up by one every block or your number goes up by one every block, you can configure Echidna to jump up to a week in time or a day in time in 24 hours. And that's really powerful because let's say you need that jump to trigger a bug, or the bug or the jump leads to the system entering a different state. You can then enter that new state and now test a little bit more. So Echidna does have the ability to fuzz block timestamp and block number. Echidna also has DAP mode, optimization mode, and a variety of different other things as well. Okay, I think that's all I'm going to say about that. I don't see any other questions, so I'm going to move on. Okay, so this is the last section of our talk, and it's about how to define good invariants. So this is sort of setting us up for what we're going to talk about next week more than anything. But it's, again, this is the most critical part about using Echidna. It's about setting up the right invariants so that Echidna can do the things it's good at. So defining good invariants, the simple solution is to start small and iterate. So what does that mean? We first define the invariants in English, and that's sort of what we've been doing for this whole time. We take the idea of total supply always has to be more than the user's balance, or Echidna caller cannot have a balance of more than 10,000. And then what we do is we take that invariant or property and we write it in Solidity. We create it into a Boolean statement that can be defined as a truthy value. So it would be balances of message.sender or balances of echidna.caller is less than or equal to 10,000. That is taking an invariant in English and converting it into Solidity. And then once you have the invariance and Solidity, you run Echidna. And if the invariants break, you investigate, you go back and you fix it. That's sort of what we did in exercise 1. We found the transfer bug, we fixed it. And then once we made the invariant pass, we went back to step 1 and we checked access controls. And access controls failed. So we can fix that as well. And that's sort of the iterative process you have to take when you work with Echidna. By the way, I guess I don't think I told the fix for part 2. So sorry for the hard pivot. But really, all you do is you just get rid of this function. That's not necessary. You shouldn't be able to take ownership by just calling the owner function. Um, anyway, okay. So how does that really work in practice, right? Recapping here, we're talking about how to define good invariants. How does that work in practice? So we like to define two different types of invariants: function level invariants and system level invariants. Functional level invariance is what we recommend always people to start with. And so when I say functional level invariant, just think of I am testing a single function. And the reason why that's easier is because a single function may not always have to rely on much of the system, or in fact, it could be stateless. It could just be a view or pure function, and that's really easy to test. So you can test it in an isolated fashion. And this is in contrast to system level invariance, where you need to deploy the whole system to be able to test the systems or the system level invariants or the things that matter at the system level. And so examples of system level invariants are users balance should be less than our total supply. Well, we've talked about this already, but think about the things that go into the understanding this invariant. A user's balance is a function of transfer calls, allowances, mints, burns, whatever other unique functionality that the ERC20 token has. So there's a lot of things that go into trying to test that system level invariant. And so it makes a lot more sense. Let's say that is the goal you want to get to. The way we would approach it during an audit is we would individually test each function along the way. We would test transfer from by itself, test transfer, test allowance, test mint, burn, whatever, and test the function level invariance of the properties. For example, transfer again, if you send from A to B, A's balance should go down, B's balance should go up. That's the truth or the expected behavior of the transfer function. And then once you do all that, you have a much better understanding of the system, and then you can test the system level invariance. And in fact, because you did all that additional legwork in the first place, you actually probably deployed the whole system already, and now you're good to go. An additional example is like yield is monotonically increasing. So you have some kind of yield system, and your yield should always be monotonically increasing. Before you actually test that, you'll probably just test the functions that actually calculate yield, right? You'll check, make sure that the arithmetic is correct through a variety of different means. And then maybe you'll come back after you've deployed the whole system to say, okay, now I have a user, he's going to make a bunch of calls. I just need to make sure at the end of all these calls, his yield has increased or it's monotonically increasing. So really important. Functional level invariance is something that we'll talk a lot more about next week. And system level invariance is going to be the highlight, in addition to functional level invariance for parts 3 and 6 as well. So a lot more to cover on these aspects. Here's an example of functional level invariant. Again, we're using assertion mode here. We're asserting something. Same exact thing though. We take in two values, A and B. Note that these are values that are free values. These can be fuzzed by Echidna, so you can make these anything from 0 to UN 256.max. And so test math, the target contract will inherit math, and we'll just assert that adding A plus B is equal to adding B plus A. And you see that this is basically, it doesn't rely on anything else. It doesn't rely on subtraction, on any token values, nothing. It just takes in two values, it does some arithmetic, and then asserts that the values are equal, right? Very easy to do. And it always makes sense to start with things like this. They're doing something like this. Now, this is a system level invariant. Again, like I mentioned, the balance of a user has a lot of things that play into it. It has a lot of different aspects that might affect the balance of Echidna caller. Now, in our example, there was only one thing, it was a transfer, but realistically, it could, again, be allowances, transfer froms, mints, burns, whatever it may be. And so it wouldn't make sense to do something like this assertion over here unless you have a greater understanding of all the other functions in the first place. So because this is stateful and requires a proper tracking of balances and understanding how balances, the mapping, is affected with all the other things, system level invariance usually requires some kind of setup. So we did some little setup in our examples. And so for those, we just deployed everything in the constructor, boom, great, easy to go. And even for like medium level, even for slightly more complex stuff, you can use the constructor to get your stuff going. However, for more complex systems, sometimes what you can do is leverage unit test framework. Let's say you have a deployment fixture. You run that with our one of our other tools, Athena, and the output of that can then be provided to Echidna to get started without having to worry about doing all this initialization. This is a simple example, but trust me, it can get a lot more complicated. And just note, to be completely frank, that initializing and setting up systems for fuzzing is arguably one of the most important parts, because setting it up correctly will, again, set up Echidna properly to do what it needs to do. I do also want to note that functional level invariants may also need system initialization. For example, let's say you're testing a deposit function, right? Again, functional level invariants focus on a single function. So I'm testing the deposit function, and the deposit function will transfer from some amount of tokens from me to the contract. Now, I need to be able to mint those tokens to be able to allow the transfer from to work, and you need allowances for that. So those kind of things are the initialization you might need for functional invariants. Again, we'll see this next week when we do part 2, and we'll focus a lot more on initialization, functional invariants, and all that jazz. Okay, so we're going to go back to the original example of the by and valid by function, and we'll go full circle and talk about how Echidna can find the bug in there. Before we do that, I'm going to check again for questions. Um, okay, so the question is, how does the fuzzer retain a test to mutate it further? Yes, I don't think I explained this really well, so I guess I have another opportunity. Um, um, Echidna has this basically tracks coverage. Think of coverage as basically like this array of just zeros, right? So let's say you have like 100, the length of your bytecode is 100, or let's say your contract is 100 bytes long. The coverage map will be 100 bytes long. And whenever you enter a piece of code or you enter a new instruction or something that hasn't been touched before, you'll set that value to 1. You'll in the byte array of 100, you'll set at some index you'll set it to 1. And that is what we define as new coverage. What that means is Echidna found something different than what it had previously. If you found new coverage, you store that transaction sequence in a different data structure. And we call that the corpus. The corpus is interesting stuff. It's the stuff that Echidna found to be cool. And the way you find something that's cool is you check whether coverage increased. Well, let's say at index 50, the value in the byte array was 0, it became 1. That's increased coverage. So that's an interesting example. Now, when Echidna wants to reuse it, it'll take something from the data structure, it'll deserialize it or deserialize it into an object that it can work with, and then it'll mutate stuff along the way. How that works exactly is kind of like a bigger question. It's if it's a uint, we'll do something differently. If it's a if it's a string, it'll do something differently. If it's an address, it'll do something differently. And so the mutation part is one of it. And then there's also something we call splicing, where when you have a sequence, you can add stuff in the middle of the sequence or stuff after the sequence. Think of it as sort of like educated randomness. Like you have information from previous runs, and you use that information to make the next decision, if that makes sense. Okay. Um, Alrighty, I don't see any more questions here, so I think we can move on to revisiting the original example. Time check, let's see. Okay, so how can Echidna find a bug in this? To refresh, we have this buy function. It takes in a tokens value, and basically you're trying to buy some tokens. To do that, the valid buy function is called, and it'll make sure that you sent at least a tenth of the amount of way given how many ever tokens you want to buy. So if you want to buy 1,000 tokens, you have to send it 100 way, and so on. And then note that if this required statement passes, which means the transaction doesn't revert, you'll mint. So by getting to this line, the valid buy function worked. So how would you actually start testing this in the first place? So um, we'll notice that the buy function is sort of stateful. You have to call mint, which means you probably have some balances, data mapping, you have total supply and all this stuff. So it seems like a little bit more complex, and it also depends on this valid buy function. The valid buy function, though, is completely stateless. It's a view function. It just takes in 2 values, and then it does some arithmetic, and it either passes or fails. In fact, I could just copy the valid buy function, put it in a different contract, and test it completely in an isolated fashion, and it would work totally fine. And that's sort of the idea of functional invariance. I can start with valid buy and build up from there, and then maybe I can indirectly test buy as well at the same time. So that's what we'll do. because valid by is stateless, we'll start with valid by. Okay, so what invariants exist for this function? There's a bunch of them, and what the one we're going to focus on, or this is again something we'll do in audits, is say, okay, what are the most important invariants for this? So one of them, for example, is if I give you no, if I set if waste sent is 0, if I give you no money, I should not be able to get any tokens out. So basically, I should not be able to mint tokens for free. Is or I should not be able to mint tokens for free. Is sort of what we're testing here. But the way we're doing it is by saying if waste sent is 0, then desired tokens should also be 0. And so that's the invariant. If I send you nothing, I should get nothing back. That's it, right? That's again what we're testing. So we can do this again in assertion mode. And we're going to say assert no free token. We take in the desired amount value, which is how much this is a fuzzable value again, which means Echidna can set this value from anywhere between 0 and un256.max. And here is what we talked about before, a precondition. The precondition here is that desired amount must be greater than 0. What that means is I know if I set this to 0 and this to 0, this will pass. And I don't really care about that because, well, hey-o, I don't know what happened there. Because I know if I send 0 to this and 0 to this will pass. And that is not really relevant to me. What I really want to test is if I set this to 0 and set this to non-0, can I somehow still pass this? And so that's sort of what the precondition does. It says, look, I don't really care about the 0 point. Doesn't matter to me. So Echidna, make sure if you want to get to this line, you have to give a value for desired amount that's more than 0, right? This is bounding the calculation zone. This is saying I don't care about the 0 where desired amount is 0. And then we'll call valid by with a non-zero desired amount and the 0 value. And note, again, if you pass through this require statement, if the value in here is true and the require passes, valid by will pass through, and then we'll get to this assert false. Because this should never happen. There should be no way I give you 0 tokens and I get more than 0 out. So when we run this with Echidna, assert no free token with 1 passes. And the reason that happens, so we have 1 here, that passes this, and we call 1 here with 0. What happens is there's a rounding error. When you do here, this is 1 and this is 0. If I do 1 divided by 10, in Solidity, that cannot be represented as an integer. So that actually truncates down to 0. And then you sent 0 in, so waste sent is 0, and 0 is greater than 0, which is what this will be as well. And so I was able to mint a token for free. In fact, you can do this for up to 9 tokens. You can do 9 divided by 10, still not representable by an integer. So you get 9 tokens for free. And you can keep doing this. And so notice how we tested valid by, but we found a bug in valid by, which actually indirectly impacts by as well. And so we were able to use a function level test to kind of cause a ripple effect and also almost cause a system level invariant to be violated, which is, and the system level invariant could also be similar, which is, this is more concrete, but it could also be, I should not be able to mint tokens for free. Okay. Conclusion, we did it. Thank you all for joining. I want to talk about a few more points before we wrap up here very quickly. So again, summary, just keep these in mind. Property-based testing aids in identifying logical flaws. So again, all 4 testing techniques are incredible, all very important. Property-based testing adds that extra oomph that you need to find the more difficult logical flaws or the hard to find code bases. And it's something that we see in a lot of mature clients. Echidna's inputs are a target contract and or one or more properties. So those are the 2 inputs. Always remember, Echidna needs something to fuzz, and then it needs something to test. The something we're testing here is not to crash the smart contract, it's properties. Echidna outputs whether or not any of these properties failed, right? That makes sense. That's the output. We want to validate or invalidate the properties. And properties are simply Boolean statements. They're either true or false, and that's it. Basically, you take English, you say total supply must always be greater than a user's balance, convert that into a Boolean statement, and that's a property. It's a truth. And you can test properties in property mode or assertion mode, and we'll talk more about assertion mode as well as property mode in the future workshops. Okay, so next week we're going to fuzz ABTK math, which is a fixed point math library. And the key focuses here, aside from the fixed point math library aspect, is to do function level testing. We're going to fuzz functions outside of the ones that we did today, which were more system level properties. We're going to do test some mathematical properties like symmetric property, commutative property, all that stuff. And then even more importantly, I would say is debugging and optimizing your fuzz tests. And so this is a really critical part, and you'll see why next week. So those will be the two focuses: functional level testing and debugging and optimizing your fuzz tests. Okay, last thing, I know we're slightly over time. Your homework assignment is, if you feel comfortable with this stuff, feel free to complete exercises 3 to 6 in building secure contracts. They get slightly more complicated, a little more interesting. So definitely take a peek. Just note that everything in here, these slides, everything are in the Echidna streaming workshop repo, and all of that stuff will be moved to building secure contracts. But we'll provide more information on that later. But building secure contracts has a bunch of other stuff in addition to just this. It has an incredible amount of resources on how to build secure smart contracts, as well as information for other tools as well, or sorry, other platforms. And then feel free to start reviewing ABDK math if you're just curious in general. We'll look at it a little bit next week. And then join Empire Hacking. It's a Slack channel that we maintain. That's the link for it. And join the Ethereum channel if you have any questions at all. And if you have questions for me specifically, feel free to just tag with @Anish Naik, my name, and I'll go ahead and respond to you guys. This slide deck is also in the same uh, GitHub repo that I mentioned at the start of um, the presentation. So you have all these slides, you have all the information you might need for part one. And note again, we're continuing to develop all the other parts. So stay tuned. You'll see a lot of pushes and commits in the next couple weeks. Okay, thank you very much for joining. This is very fun. This is exciting that we're doing this at TrailofBits. I hope you guys liked it, and definitely come back for the future workshops. I'm going to pivot over to see if there's any other questions. Looks like we're good. And so yeah, the next stream will be on Tuesday, November 22nd, 12 p.m. You'll be with me again, and then the remaining streams will remind you again next week as to when that third one will be. But again, thanks for joining, and hope you guys enjoyed it.